Hi and welcome back to Organic Chemistry Module 7. Today we are looking at the structural formula, the properties and the functional group of our aldehydes and ketones, our amines and amides and our carboxylic acids. So far we've been looking at the naming of them, their structural formula and so forth, but we haven't really looked at what properties they have and how they compare to the alkanes, alkenes and alkynes, as well as our alcohol groups. So that's where we're going to go with today's little lesson. So starting with our aldehydes and our ketones, remembering these functional groups have the double bond to an O. The only difference between them is their placement of that double bond O, with our aldehydes or alkanals always being on the terminal carbon on the ends and our ketones being within the middle carbons. So we call that double bond O a carbonyl group. So here's just to refresh your memory, just in case when we were doing our naming you've forgotten. Here you can see we have the R, meaning we just simply have there our a hydrocarbon. We have our C, double bond O, and you can see there that it is the end carbon. Its condensed formula is CHO. Don't confuse it with the alcohol group, that's an OH. Ketones are different because it's not on an end carbon. So what are their properties? So we look at oxygen. Oxygen's more electronegative than carbon, so the difference between them means that it has a tendency to attract more electrons in that carbon-oxygen bond, so it makes it polar because of that difference. Because of that polarity, the dipole-dipole forces acting between them are there. So that's creating that difference in those forces there. So what happens because of those dipole forces is that we have higher boiling points than we would have normally gotten in other similar molecular masses. Hydrocarbons only have those dispersion forces, so they don't require as much energy to break those dispersion forces, therefore they have lower boiling points and melting points, whereas these guys have those dipole-dipole forces and they are stronger and therefore harder to break, requiring more energy, resulting in a higher melting point and boiling point there. So, as I've just mentioned, they have higher boiling points than some of those other compounds of similar size. However, they do have lower boiling points of alcohols. Now, why do you think this might be? Think of the bonding that we have on the side. We've got the hydrogen and the oxygen, and there we're getting our hydrogen bonding. And our hydrogen bonding is even stronger than our dipole-dipole forces, therefore requiring more energy to break those. Now, the fact that we have a carbonyl group and it being polar means that it is forming a fairly good attraction there with our water molecules that are also polar, and that makes them more soluble than our normal hydrocarbons like our alkanes and so forth, but less soluble again than our alcohols. Again, similar to the alcohols, as the hydrocarbon chain increases, then that hydrocarbon chain is outweighing the polar end, and then our solubility will decrease. Looking at our carboxylic acids, we have now got our C double bond O, and then we've got our OH there in the corner. Now, interestingly, a lot of these are found in nature. Methanoic acid, our most simplest carboxylic acid, otherwise known as formic acid, is actually present in an ant bite. If you think of acetic acid, it is also ethanoic acid. It's present in our vinegar. Butanoic acid, otherwise known as butyric acid, you might have heard us mention that one before, is that vomit smelling acid that we do have, and it's often that smell that you get in that off cheese. So many of these acids have strong, unpleasant odors. So here we've got a carboxyl group, not to be confused with a carbonyl group. A carbonyl group is just the double bond O. A carboxyl group is a combination between carbonyl and hydroxyl, meaning OH, and because they're combined together, we're getting our carboxyl group. So what happens with these guys? And in here, we have the OH group and the C double bond O. And because we've got those there, we're going to get some different sort of features. The carboxylic acids can form a whole range of intermolecular forces there. We're going to have the hydrocarbon chain, and in our hydrocarbon chain, we're going to get the dispersion forces. The C double bond O part is going to have dipole-dipole, and the OH part is going to have hydrogen bonding. So therefore, we're going to need more energy to overcome all these intermolecular forces between different carboxylic acid molecules. So they're going to even have even higher boiling points than any other group of a similar size. So if we were to compare 1-propanol, it has a boiling point of 97.2, while ethanoic acid, similar mass, has a boiling point of 118. So you can certainly see there a difference in their boiling point due to the different types of bonding that are present in the carboxylic acids compared to those of the alcohols.